Okay, so kia ora everybody, and welcome to UC Connect lecture tonight. I'm going to start off, I'm supposed to do some housekeeping. So the loos, very important, I think out the door and around the corner, or out that door and around the corner. If the fire alarm goes, we follow people who seem to know where they're going, probably with the UC staff written on them. We'll go out just out the front and out the exits. If there's an earthquake, in the unlikely event that there's an earthquake, if there's shaking, we can all take cover for a few seconds till the shaking stops, and then we can go outside. If a volcano erupts, definitely don't follow me, because I'll probably be running towards the volcano, and that's probably not correct health and safety procedure. So kia ora, ko Fel Beacon te monga, ko the ooze te awa, ko Sumner te papa, ko Ben Kennedy tohu inua. So I grew up in the UK, running around the South Downs and hammering chalk and making a mess, looking for fossils. Jumping in and out of the very muddy and appropriately named River Ouse. But I've since settled in Sumner, and with my lovely family here, Sina and the boys, and we live in a house with volcanoes painted on the front fence. So I am living the dream. You know, it's pretty much a dream to come to Aotearoa and to be a volcanologist. These are my feet dangling out of the open door of a helicopter flying over Whakaari, White Island. And you can imagine that's quite fun and quite exciting. I get to take selfies of myself with volcanoes erupting in the background. This is in Vanuatu, and me and Matt were flying drones over this erupting volcano, mapping where bombs were landing and going splat. So this is what the talk is about. Why drill into magma? So I would argue that magma is the final frontier. You know, we've been to the moon, we've been up into space, but we've never been into magma. And we don't know what it's like. We don't know if it's mainly liquid or if it's mainly crystals. We have a very bad idea of how big magma chambers are, or how big they can get. So I think, you know, it's a real, you know, why should you do this? It's the same reason that we went to the moon. We are curious. We are human beings. It's what drives us. I would also argue that living somewhere like New Zealand, knowing about magma is potentially more useful than knowing about the moon, because magma in New Zealand has the potential to annihilate half the country. It also has the potential to provide cheap, sustainable energy for the country as well. So it's a pretty important thing to know about. So I want to approach this talk a bit like a storyteller. And I argue that volcanologists, at the moment, we are not that much more than storytellers. We don't know that much about what magma does underground. And so we create models, and we try and use those models to tell a story about the volcano. And you know, and in a similar way that the Maori Korero and the Parako tell stories about what causes volcanoes. In this case, it's Ruomoko wriggling around in his mother's belly, causing earthquakes and volcanoes to erupt. So I think we can learn a lot from the Maori approach to telling stories as scientists and as science communicators. Stories are a very powerful way to get messages across. So I'm going to try and do a bit of that today. So one of the things as volcanologists that we're supposed to do is forecast when eruptions are going to occur. Forecasting what's going to happen at the end of the story. When's it going to happen? And if you have a nice simple volcano like this, with a magma chamber 10 kilometers deep, and a simple volcano, and say there's some earthquakes down here, we think magma's on the move, we know that magma is rising at, say, 10 kilometers an hour, we know the volcano is going to erupt in an hour. Easy job. But volcanoes tend to look a bit more like this. There's not one simple pathway. There's not even one magma chamber. There's actually a whole series of pathways in magma chambers, which makes it fun to be a volcanologist because I get to tell lots of exciting stories and there are lots of possibilities. But it does mean that eruptions are hard to forecast. And the other question we're asked as volcanologists is, what's going to happen? How big is the eruption going to be? And so there's a whole range of different eruption styles you can have coming out the top of your volcano. You can have booms, throw lots of ash up into the air. And you can have splats and lava flows that are a bit more runny. Or, of course, you can have geothermal energy. So it's up to us to try and work out which one of these things could potentially happen. So you are going to be tested. Normally I don't get this many people turning up to my classes, so I'm quite chuffed. But yeah, I'm going to be asking you questions, and that's why you've got the cards in front of you. So just to recap, ash goes boom. It's generally from cooler, stickier magma with lots of gas in. Lava can flow or go splat, and it's from hot, runny magma, which isn't so gassy. So a lot of what we've learned comes from experiments. So I have a lot of fun labs here in New Zealand, and I work with people abroad where we do experiments. And yeah, they're fun and you learn a lot, whatever age you are. So I'm just going to show, so remember, this is going to be on the test. So we're starting off with the lava lab here at the University of Canterbury. So I have this rock that some of you have seen. So this is a bit of homemade lava from the lava lab here in UC. And you can see it gets pretty hot in the lava lab. So this is 1350 degrees C. And we literally melt rocks, and we keep those rocks hot and runny by maintaining those high temperatures. And this gives us the ability to make lava by keeping the magma hot. Okay, so now it's time for your cards. So you've all got cards with letters on. And the first question, start off with an easy one. So, lava needs to stay hot to become a runny lava flow. Is this true or is this false? So raise A cards for true and B cards for false. Okay, that's looking pretty good. Most people have got A. We've got a few rogue people out there, but most people have got A, and it is true, right? We want to make lava, we need nice, hot, runny magma. Okay, so now, here is me in my spaceman suit in Hawaii, and I've just scooped a bit of lava out of a lava flow, and you can watch that lava gradually cooling. As it cools, you start to form crystals in it. Okay, so you can cool down and you can crystallize, and you can actually change the composition of magma, okay? So, a magma without much gas that is cooler and crystallized might make A, geothermal energy, or B, lava. Okay, this is kind of a hard question, and we've got a bit of a mix here, okay? We've probably got about half and half, okay? So what I'm getting at here is, remember, for lava to come out of the volcano, it needs to stay hot and runny. So what I'm getting at here is, for magma to stay underground, it needs to crystallize. So I was going for you guys to answer geothermal energy, because we wanted to keep that magma underground and not let it erupt as runny lava, okay? Wouldn't be fun if you got it right every time. You wouldn't learn anything. Okay, so we've also got a lab where we can put gas in and out of magma. So gas is another really important thing. You've got temperature and you've got gas. And so we've got the magma brewery at UC. And in the magma brewery, we can actually pressurize magma, and we can dissolve gas in it. And then you can decompress the magma slowly, and you can grow bubbles. So that's like a little bit of magma popcorn, bubbles growing in your bit of molten rock. So this is getting gas into your magma, okay? So which of these eruptions needs cooler, sticky magma, but also gassy magma? Okay, again, we've got a bit of a mix, okay? So, gassy magma is this rock here. Anyone know what this rock is? Pumice, okay? It's pumice. It's pumice, it's got lots and lots and lots of gas in, okay? And it comes from quite a sticky magma, okay? So, and big boom eruptions, this actually came from Topor, so big boom eruptions are from gassy, sticky eruptions. Something like this, that looks suspiciously like a cowpat, without the smell. This is from a splat eruption. And you're right, you do need a bit of gas for a splat eruption, but you also need it to stay hot and runny in order for it to form a splat, okay? So everyone's clear? The answer I was going for here is big boom eruptions have gassy and sticky magma, okay? So hopefully we're learning something here. So you can also lose gas. And I can do the same experiments in my magma brewery, where we can heat up our rocks again. And instead of growing bubbles, you can see the bits shrink, because they're actually losing gas and the bubbles are coming out of it. It's densifying, okay? So you can lose gas as well as gain gas. Okay, so which of these eruptions do you think needs cool, sticky magma that's lost most of its gas? Okay, raise your cards again. Okay, looks like we're learning something. Got lots and lots of B's here, so that's good. So small eruptions have less gas in them than the big boom ash eruptions. Okay, so another thing that is incredibly good fun to do is popping balloons in with high-speed cameras and letting the bubbles make a splash. So this is actually, well, also I won't give the answer away. So if we watch this video, if you burst a balloon, let the bubble hit the surface, it makes a splash, okay? And if you get stickier and stickier fluid, so this is now quite a sticky mud, you can start to create cowpat bombs flying through the air, okay? And you can vary the stickiness and make different size and shape bombs. Learn more about how volcanoes erupt. Okay, so which of these needs hot magma that splashes when a bubble pops? The big boom, the lava, the splat, or the small boom? Yeah, I can see lots of red. It's like at a rugby game. Yeah, so the answer is splat. You can make those lava bombs when a bubble pops at the surface and ejects those lava bombs out. So another thing we can do is in Germany, they have an amazing machine where they can actually decompress pumice fast enough to generate ash, and not only generate ash, you'll see what else they can do. So I work with these guys quite a lot. This is back in the day when dyed blonde hair and Hawaiian shirts were in fashion. Okay, so let's watch the video. So this is a pumice that's now decompressing, and all the gas is rushing out, and it's turning that pumice into ash. And the ash particles are now flying out the top, and can you see what that is? Micro volcanic lightning. Like, how cool is that? This was a surprise. So the lab was not intending to make lightning. They just got better and better high-speed cameras, and they discovered that they were making mini lightning bolts in the lab, which is pretty cool. And if you've ever seen some of these spectacular kind of National Geographic style videos of big volcanic eruptions, you get lots of lightning. So explosive decompression. So which of these needs gassy magma to decompress and create ash? Big boom, lava, splat, or geothermal? Okay, it looks like we've got mostly A's, and that's the answer I would go for as well. Big boom, okay? That's where you need that explosive decompression to create lots of ash, and that's kind of eruptions. Now here's another very cool experiment that my friends do in Liverpool. So you can also get earthquakes associated with volcanoes. And my friends in Liverpool have just discovered that when an earthquake occurs in magma, and you create a fault, and this fault slips against each other, an interesting thing happens. So now we're spinning two rocks against each other, two volcanic rocks, just like the friction that's occurring during an earthquake. And you can actually create magma. So you can see, rub your hands together, gets hot. You can actually create magma this way. And we've learned that not only do you create magma, you can actually create a few bubbles in that magma as well through this process. Okay, so which of these needs an earthquake to create friction in a gas poor, cool magma that can still cause an explosion? Big boom, small boom, splat, or geothermal? This one's a bit harder. You can confer with your friends. You're allowed to. You can phone a friend. Okay, so we've got a bit of variation, but looks like we've got a mixture between B's and D's. And yeah, I would go with B's. You're getting these small boom eruptions. You can generate these small eruptions from friction. You can get small booms associated with geothermal energy, but it's not usually that kind of from friction generating melts. And this is a relatively new process. I could probably ask this question to the top volcanologists in the world, and most of them would get that wrong, so you're doing pretty well. And this is another test we do. So we have cores. You'll see cores like this, and you can squash volcanic rocks. And as you squash a volcanic rock, the rock can't take the stress. So this is an experiment that we can do both at UC and in Liverpool. And this is a core being squashed. And you can see, boom, as it squashes, it eventually fails. So which of these needs the compression of a relatively gas-poor cool magma to cause the rock to shatter? Okay, looks like most people have worked out by a process of elimination that we haven't talked about sideways boom yet. That is exactly correct, and you could kind of imagine that thing was shattering out towards you. Okay, so from doing these types of experiments, we learn, we can develop equations of when things happen, and from making observations about what happens at the volcano, we can put this together into a model. But it's still quite hard to know which way. No model can really predict a complicated situation like this with all those different possibilities. So this is where our drill hole into magma could come in handy. So if we had a window deep down into a magma chamber, and we could sample a bit of that magma, we'd know a bit more about it. We'd know if it was gas poor, we'd know if it was hot, right? This would help us work out what's going on. And this is, it looks like a comic book, okay, but this is actually happening now. So there are a series of governments around the world clubbing together to try and build a research facility to drill into magma. And this is some associated material that we're developing for schools as well to help school kids learn and get excited about this project. Still haven't secured all the funding yet, so if we have any millionaires in the room, come talk to me afterwards. Okay, so now it's time to meet Rua. Rua, the magma brewer. Rua is the creation of Janina. Say hi, Janina. Janina's our volcano artist. So Rua is going to go on a journey through the Earth, and you are going to be scientists, and you are going to use your cards to guide Rua through the Earth to your eruption of choice. So remember, if you look at your cards, you've all been assigned a team. At the top of your card, it should say something like Big Boom Team, or Lava Team, or Splat Team. So once you've worked out what team you're in, your job is to try and guide Rua towards what your team is all about, what explosion style, okay? So I'm going to be asking you questions, and you guys are going to vote, and whoever gets the most votes, we're going to make a decision, and we're going to follow Rua in that direction. So, and we're going to use our windows, okay? Our windows to help us decide what Rua's going to do. So we'll start off with Rua down here, and I want you to vote whether Rua will stay hot and runny, or whether he will start getting stickier, okay? So think about where your team wants Rua to end up to decide what you want to vote. Okay, so we've got a lot of bees back there, a lot of bees. It's pretty close. I think I'm going to go, I think the bees have got it, okay? We're going to go. We're going to click on Get Stickier. So here is Rua, and Rua is slowly crystallizing. It's growing crystals, and he's getting sticky like toothpaste. So let's see Rua where he goes. You see he's turned white now. He's got a bit cooler, he's got a bit stickier, and he's moved up in the world. So now we're looking through a midway magma window, and he's sticky and he's more silica rich. So now we've got to choose. Do you want Rua to decompress, or do you want Rua to lose gas? Okay, raise your cards up high. Oh, it's looking quite close again. We got lots of bees in the middle. I think bees have probably got it again. Okay, so we are going to click on lose gas. So there is Rua. Hold your noses, Rua is losing gas. Volcanic gas tends to be quite smelly. So Rua has now moved up to here. And now we're in a shallow, sticky magma window, and we haven't got much gas. Okay, now we've got 4 choices on what to do. Okay? So let's vote on what you want Rua to do. You might not be voting for your team, you might just be wanting to see what's going to happen. Okay, let's see what we got here. Okay, there's a lot of A's at the back. A lot of A's around here. We've got a big D section. I think A's are winning. What is A? Okay, A is decompress. So let's see what happens when we decompress. Here we go. Feeling the pressure. Time to release. Rua's going up here. And we've created a medium-sized boom. So team medium boom, give yourself a round of applause. Well done. So what does a medium-sized boom look like? So this is Mount Cucino Irebugima. And this is only a medium-sized boom, but it's quite spectacular. So if we just watch that again, you can see ash is being fragmented, just like in the lab. And now it's actually, the ash is actually descending down the volcano and starting to generate pyroclastic flows. Luckily, they'd evacuated this volcano. Not that many people live on this island, and they'd evacuated it before that happened. Okay, so maybe we'll just explore some other options. So let's see, he wants to see what happens when we shear. So here's our shearing. Again, we're making our nice magma. And what would this look like? See, up here, he's relatively gas poor. He's formed a little lava dome on the side of the volcano. And you get a small boom, okay? And to see what a small boom looks like, this is a video that my old PhD student Felix made. So he was flying his drone above this lava dome in Guatemala. And he was lucky enough to see this. And if you notice the camera shake there, that's the sound wave hitting the drone and making it shake. We can watch that again. They see that there, they see those 2 lines. So that's one of those faults slipping and generating that ash along a fracture. Pretty cool eruption. Okay, so if we freeze, our rock cools down, and Rua ends up over here, creating nice geothermal energy for everybody to enjoy. Nice mud pool. This is up in Rotorua. And a mud pool that's being heated up from below by magma. And then we haven't tried C. This is what happens. Oops, sorry. When we shatter. Lots of geology puns. And here he goes up to his lava dome again, and the lava dome produces a sideways boom. And what that looks like, here is a lava dome in Montserrat. And you can see when bits of this glowing lava dome shatter, you create these pyroclastic flows that come tumbling down the volcano. And it's these pyroclastic flows that actually, one of the major things that on the island of Montserrat, that 2/3 of the island had to be evacuated because of these ongoing hazard from these pyroclastic flows. Okay, so let's try some other options. Oops, no, that was the wrong thing. Let me go back in. Let's go back to the start, just to explore. Okay, now let's go, should we follow the hot and, let's try, everyone work on the same team. Your job is to make lava, okay? You're now all on the lava team. What should we do to make lava? Hooray, everyone is now united with an A answer. Here he is, staying hot and runny. And going up this way. And now we're looking through our window, and what do we, okay, this is, so think about this. Now, do you want to form lava? To form lava, do you want to lose gas, or do you want to do a bubble splash? Looks like most people are going with, it's about half. Most people are going with A, I think. We've got quite a lot of Bs, okay? I'm going to go with A. So here he is, he's losing his gas. Oops, well, we've seen what he looks like when he loses gas anyway, so let's see that. And losing gas, hooray, you make lava. And there is Eldra coming through in his lava flow. And let's also have a look what splash looks like. This is actually one of my favorites. So here is my mud bursting balloon. I did get hit in the face by mud balloon explosions while doing these experiments. And here we go, the splat team. And this is what a splat eruption, so these are like those eruptions in Vanuatu. And that is a nice glowing cowpat from one of those bubble bursting, producing a bomb. So the only one we haven't done is, which one haven't we done? Big boom, so let's go back here. How do we find our way to big boom? A or B? B. It's cooling down. Okay, now from here, he's sticky and he's crystal rich. Do we want to decompress or lose gas? Lots of A's. Okay, let's decompress. Here we are, growing our bubbles. So first you're growing a bubble, so our magma is turning into a bit of pumice popcorn. And from there, you've only got one choice. Boom. So, and this is what a big, so Tapapa has just got a new exhibition, so I recommend anyone to go there, and this is some of their amazing animations from Tapapa, and this is the magma chamber under Topor. So this is as accurate as we, as volcanologists, know what the Topor eruption would be like. It's a little bit of added special effects there. Okay, so let's get to the end of the story now. So I can see you've all learned a lot of volcanology. So hopefully you realize that having those windows, knowing something about what the magma was like, was actually really useful in trying to predict what the eruption might be like. And there's this amazing opportunity in Krafla in Iceland with unparalleled opportunities to do science and this amazing opportunity to get, cheaper, sustainable energy. This is the power station, a geothermal power station in Krafla. And in 2009, they were Landsvirkjun, who are the power company in Iceland, and are now working really well with scientists. So this happened. So their geothermal wells don't normally look like this. So things started melting, lots of acid gases started coming out, and when the drillers, luckily the drillers managed to keep control, and the pressure spikes were going through the roof, temperature, things were all going through the roof, and when they looked at the drilling mud that came back up, they found all this tiny, tiny pieces of volcanic glass in the drilling mud. And they worked out that they'd accidentally hit a magma chamber. And when you looked at these bits of glass, you could actually measure calculate the temperature and the gas content. And Tomiko did that. Say hi, Tomiko. By looking at these tiny chips of glass, you worked out exactly how much gas was in there. And the other really cool thing that this now shows is, you see this kind of knobbly texture on top of this chip? So this is one of those chips looked at with a CT scanner. And that knobbly texture on it not only means that actually the magma probably got quenched by the drilling mud and solidified it, and then it probably had small fragmentation events to make this. And you can see there are some nice bright green glowing crystals in there. So this window has given us unique information that we would never have if we hadn't accidentally drilled into this magma chamber. And it's also told us that we can control, in this case, the pressure of the magma. So the drill was going down slowly, and then at some point, the drill started to come back up again. And drills, when they're supposed to be going down, it's unusual to find them coming back up again. And actually, the magma pushed the drill, I think, about 9 or 10 meters back up the hole before the drilling mud quenched it, and they got control of the pressure. So, but we still don't really know. We know how deep the magma is, because we know it 2 kilometers down. That was when we hit it, but we still don't know that much about the shape of the magma chamber, and scientists are still arguing about that. Well, I'm just going to turn the lights out now, because we're going to play it on here, but I've also got a fancy hologram that may work. So some of you will be able to see the hologram, some of you may not, but I'm going to play it anyway. So we've also made a drilling into magma chamber game for schools, and this is one of where the students can choose where to drill. So let's see if this works. So here you can see the drill hole going down, hopefully, and I'll start it on the screen as well. Oh, it's got stuck. See it going down on the screen. And the idea is, what does a magma chamber really look like? And we've actually interviewed a whole bunch of different scientists trying to work out. So scientists didn't even know that there was a magma chamber there at 2 kilometers, and let alone what size or what shape it is. So this is actually my guess at what the magma chamber looks like. I think it kind of looks like a big tongue. So I think it's kind of quite a thin amount of magma. But other scientists have completely different ideas. Some people think there's a big, large volume of magma there, but we really don't know. And this is one of the reasons we need to go back there, because we need to refine our equipment to better identify magma. Not only to identify it, but to find out how big it is. And also to develop our technology that we can actually correctly control and identify temperatures and pressures associated with these magma chambers. So it's probably not a good idea to drill into a magma chamber that you don't know about. So if you have a very, very big magma chamber down there, and it's very hot magma, that magma might not stop after going down a few meters. It might start rising up the borehole. And because this is hot magma, what kind of eruptions is it going to make? It's going to make a lava flow, okay? And if it was a very gassy magma chamber, you might get a more disastrous. Here your magma's coming up, and you can imagine this kind of thing is not what the Icelandic government is after, or any government in that matter. But the amazing thing is, at Craftflow, we know what's going to happen because we've done it before. We know where that magma is, and thanks to Tomiko, we know how much gas is in the magma. We know what temperature it's at. Okay, so we have this unique opportunity in Craftflow. And the idea is to build a Craftflow magma test bed where scientists can drill holes into the magma chamber. They can take samples. They can have a series of other drill holes where they can test equipment to better identify where the magma is, what it's doing. So this is John Eichelberger's brainchild. So he's leading this group. This is John in the University of Canterbury with some Chinese and New Zealand and Icelandic colleagues where we're having a workshop trying to design what are the priorities and how can we raise this type of money needed to do this project. So in summary, we want to explore the final frontier, right? This is frontier science. It's exciting. Hopefully it captures the imagination of the next generation and inspires people to do science and to value it. It's an opportunity, just like those trips to the moon, to drive new technologies, to create sensors that can work at these high temperatures and high pressures. It should help us better mitigate hazards. Hopefully those windows and that funny game that we played shows you that it's easier to predict hazards the more you know about the magma chamber. And you can make more efficient geothermal energy. So that well, they actually used it for a few months, or maybe even, for a few months after they hit magma, and they sucked energy out of it. And it was the most efficient geothermal well on the planet because it was so damn hot. So they're making more megawatts from that well than several of the other wells put together. So it's an incredible opportunity. And I just want to thank Janina, Rob, Jonathan, Elodie, Tomiko, and all my students and colleagues. So I'll leave it there. Do we have some questions? Noah?
What's your favourite kind of boom?
My favourite, so this is Noah, my son. My favourite kind of boom, that's a good question. I think either the splat or the small boom, because they're kind of safe enough that you can watch them and learn science from watching them.
Thank you. I just wondered if magma changes over time, or is it a constant thing? So once you've drilled down to it and worked out what the gas is and what the temperature is, so that's it, or does it change?
Yeah, so very good question. So does magma change with time? So depending on how big your magma chamber is, it's going to be cooling. So it's going to be gradually crystallizing. So a really big magma chamber may stay molten for thousands, tens of thousands of years, but a small magma chamber that's only a few meters thick may cool on the order of months or a couple of years. So yeah, with time it will cool. It can also change composition slowly. So when it forms crystals, crystals can settle and it can become stickier and more silica-rich and more gassy with time. So it can change with time, but these processes take thousands of years rather than months.
Why are Erebus crystals unique?
Why are
Erebus.
Erebus crystals? So Erebus is the volcano in Antarctica, and it's got these beautiful big alkali feldspar crystals in it. I have never been to Erebus, so I don't know too much about the answer to this question, but I do have some of those crystals because one of my friends went there and gave me some. I suspect, so in order to grow a big crystal, you need time, and you need the right chemicals in the magma. So those are, Erebus will be rich in alkalis, and it will have enough time to crystallize some of those big alkali-rich feldspar crystals.
Does the volcano ash really have a biological function?
Does volcanic ash have a biological function? So ash is quite unique. So this is a bit of pumice, and when you explode this bit of pumice, you create ash. And if you look at this ash under a microscope, it's incredibly spiky, for one. So it has a very, very large surface area. And when you're creating particles with a large surface area, it's a lot of space for bacteria to hang out. And to be honest, I'm going to get into biology here, and I'm going to start getting into deep water. But yeah, I think there's lots of surface area, there's lots of unique chemicals, and if you've got the right extremophile animals or things, then these could be places for animals to live. Sorry, I don't know too much about biology of ash.
Do all the magmas start off with the same basic chemical content, and does it just vary as they change temperature and undergo pressure and things like that?
Yep, so all the magma comes from the mantle. So underneath the Earth's crust, you have the mantle, and the mantle is a kind of crystalline mush that will melt. And that will melt, and depending on how much it melts, you can create slightly different types of magma. And then that magma will do its journey through the crust, and it may have a whole bunch of changes that occur during its journey to kind of diversify to create. But most of the magma comes from the mantle, from one place.
Do different types of gases in the magma chamber make different types of explosions?
Oh, very, very cool question. So the different types of gases make different types of explosions. So volcanic gases is mostly water. So water is by far the dominant gas that comes out of volcanoes. You do have sulfur dioxide and fluorine and chlorine and other gases. But because water dominates, water is what drives the explosion. But you can get special types of explosion related to sulfur-rich volcanoes, where there may be lots of liquid sulfur around, and that may change a little bit. But mostly it's the water that causes the booms. It's a good question, though.
Excuse me. After a big boom, what are the constituents of the atmospheric substance which causes so many problems for the aircraft?
Okay, so after a big boom and we're generating lots of ash, what's causing the problem for aircraft? So I was lucky enough that one of my students works in what was he? He's an air traffic controller, and I think his dad gave me some of the ash that they'd taken out of one of the engines. And mostly the problem with ash that gets into an airplane's engine is it's made of basically of glass. So it's extremely abrasive, one. So it's glass is very strong. So it's very abrasive on engine parts. And also, if you're getting sufficient temperatures, you can actually start to melt that glass again and start welding bits of glass together. So there's abrasion and actually melting and fusing glass into the engine that causes problems for aircraft.
I was thinking about the relationship with global warming. If we thought of global warming as sort of heating the skin of the orange, does it have any effect on the stuff inside?
Okay, so does global warming affect the volcanoes? I think on the scale that we're talking about, human-generated global warming, it's probably not enough to bother the volcanoes. But if you're generating extreme climate events, generating typhoons, flooding, that kind of thing is going to cause hazard interactions with volcanoes. So imagine you drop a bunch of ash all over Taupo, then you get hit by a typhoon, all that ash turns to mud flows. So they would definitely work together in a bad way. Interestingly, volcanoes can actually offset global warming. So a volcano that chucks enough ash and sulfur dioxide into the atmosphere can actually reflect away some of the heat from the sun and can actually cool down the planet. And there was a volcano in 91 that erupted. And if you look at the climate record, in 91, it flattens off because the volcano actually counteracted humans' activity and caused cooling for a year.
Putting up an umbrella.
Yeah, it's kind of like putting up an umbrella, exactly. A reflective umbrella, yeah.
Are there any dangerous bacteria in the magma chambers?
So in the magma chamber, I don't think we've discovered any bacteria that can live at, say, 900 or 1,000 degrees C. But there was a professor in the department, and Noel, who's actually sitting over here, who was his grad student. And Noel and this professor were looking at some bacteria that can exist at temperatures, I think, around maybe 400 degrees. So they can exist around the magma chamber in the hydrothermal system in quite extreme conditions. But I don't think they've found any that can actually live in the magma itself.
I'm over here. In order to see the shape of magma chambers, what's the usual method?
Okay, so in order to see the shape of a magma chamber, one way you can do is you can let the natural earthquakes that are occurring, and you can put lots of receivers all out on the surface of the Earth, and because certain types of waves don't travel through liquids, they actually make a shadow above the magma chamber where none of the particular waves get through, and then where that shadow is indicates that's where a magma chamber is. So that's one way. You can also create earthquakes and then measure the speed change. So again, in quite crystalline magma, the speed of the waves will change, and you can use that to image. You can also look at the surface of the Earth if it's deforming. That might indicate that there's a magma chamber there. Gas, you can measure gas at the surface, see where gas is coming out. And if you could put some of these things down holes, you'll be able to get a lot closer to that magma chamber. Imagine if you're a doctor and you're trying to prescribe a patient and that patient is buried 2 kilometers underground, it's quite hard to work out what's going on. So if you can get your instruments closer to the patient, you'll be able to better work out what's going on.
Because these are three-dimensional structures, where do we think the closest magma to us here in Christchurch is? Is it below us, or is it a bit further out?
Oh, that's a good question. So how deep would you have to go? There's no magma at any shallow level beneath us here. You'd have to go pretty much down to the mantle, which is going to be tens of kilometers underneath us. So probably still straight down is going to be closer than going to Taupo or Tongariro. Yeah, and I think that I've heard a rumor that they found an anomaly in the mantle under Dunedin. So. I don't know how deep it is, but yeah.
My question's, I think I read a paper saying that you could harvest geothermal energy from magma chambers as a way to try and cool down potential supervolcanoes. Is that viable / feasible?
So I mean, I didn't put that one up on the board, but technically, if you are sucking enough energy out of your magma chamber with geothermal energy, you are actually cooling down your rock at the same time. So if you suck out geothermal energy for, say, 100 years, you're removing megawatts of heat, you're actually cooling down the magma body that's there. I think this is more of a long-term process rather than there's a volcano going to erupt, let's suck out all of its heat. But maybe over hundreds or thousands of years of extracting energy, you would actually cool down the magma chamber and reduce its chance of eruption.
When magma's moving through the ground, I mean, how does it move? As in, like, is it going through pre-existing cracks and holes in the ground, or is it like drilling its way through by melting its way through?
Yeah, great question. The answer is mostly moving through cracks, that's why you can hear magma moving, because it's moving through cracks and it's propagating cracks and they're making small earthquakes. So it's mostly moving through cracks, but we can look at the chemistry of some of our magmas, and we can see that it does also dissolve a bit of rock along the way, and it'll depend on what rock it's moving through. It can break off chunks and dissolve them and change its chemistry slightly as it moves through.
So you mentioned with the Krefler drilling and accidentally getting the magma chamber, that it was a surprise. But like when you showed where you get geothermal energy, it's when you have a magma chamber underneath. So why was it a surprise?
Yeah, so good question. So why was it a surprise? So it wasn't a surprise that there was magma there. They were just expecting it to be at 4 kilometers down rather than at 2 kilometers. So it was a surprise that it was that shallow and in that part of the system. Yeah, so I mean, yeah.
You mentioned an explosive volcano has probably got water in the magma. Where does the water come from? How does it get there?
So the water that's in the magma, so where does it come from? It comes from inside our planet. So there's water basically outgassing from the magma. It's been happening since the planet was created. It's a good thing to think about. People like to say we're all stardust, but I like to say we're all magma, right? All of the ions in your body was once inside the planet and part of magma, and it's that gradual escape of all those elements as gases and magma that's created all of the elements that make us up, including water.
Can we see magma chambers, like fossil magma chambers? Where would we go? Banks Peninsula?
Yep, so anyone been to Inawi Peninsula? So at the end of Inawi Peninsula, there's a small magma. Basically, if you see granite, that is a crystallized magma chamber. At Inawi, there's a rock called syenite. But even when you see, even up where there are, we call them dikes, where you get magma frozen in a vertical structure, that's frozen magma. So yeah, lots of places all over New Zealand you can see frozen magma.
Is there any eruptions that can cause volcanoes to explode themselves?
An eruption that can cause the volcanoes to explode themselves. So maybe a triggered eruption. So maybe can one small eruption set off a bigger eruption? So lots of eruptions may start off with a smaller eruption, maybe not of magma, but just of gases from the hydrothermal system. So one eruption can trigger another eruption.
If you drilled into an extinct volcano, so if you were drilling in Auckland, what would you see there? And my second question is about fracking. Does fracking create a problem for volcanologists?
So if you're drilling into, so lots of people all over the world have drilled into extinct volcanoes to learn about their eruption history. So if you're trying to work out what a volcano might do in the future, you kind of need to know what it's done in the past. So by drilling into it, you can see all the different layers that of how it's erupted previously, and you can use that to work out what might happen in the future. So it is a useful exercise to drill into an old volcano. If there are hydrothermal steam and gases around, you'll have to be obviously very careful that you don't get small steam explosions. But yeah, and then your second question was about fracking.
Is that creating new fissures and cracks and things that make volcanic activity?
Yep, so I guess there's so the petroleum industry can use fracking in order to create cracks in order to extract petroleum products. Generally, they don't do that around volcanoes. They'll do that out in a nice sedimentary basin where the petroleum is accumulated. In geothermal drilling operations, fracking can occur as a natural process. Fracking just means you're creating a crack in a rock, and if you've got lots of steam down there, you're going to be creating cracks, and that's actually how you get geothermal fluids out anyway. So it can occur in a natural way, or you can do it in nasty ways where you pump nasty fluids down and cause pollution. But there's different ways of doing fracking, some that are more better than others.
How do you tell how deep they are?
How deep the magma chamber is? So that's exactly what we're very bad at doing. At the moment, we can't. But you can see earthquakes. You can locate how deep an earthquake is occurring. And if you know that that earthquake is related to magma trying to squeeze itself along a crack, then you can locate where that crack generated by the earthquake is occurring, and you can say, okay, that's where we think the magma is moving.
You said that magma chambers can turn into granite. If there was a giant magma chamber, would it make a lot of granite?
A giant sticky magma chamber would crystallize to make a lot of granite. So if the kind of places like Yosemite in the States, these beautiful granite cliffs, these are huge magma chambers that form very deep in the earth a long time ago, and they've since been eroded by glaciers and exposed these big granite magma chambers. One more last question?
Okay, just one more.
What's next for New Zealand? Are we going to see another Rangitoto or another Lake Taupo? And what can you tell us about the difference between those two types of eruptions and likelihood?
Okay, so best to ask that question to GNS Science, who are monitoring the volcanoes. All I can say is from looking at history of what's happened in the past, some volcanoes erupt more often than others. So, for example, White Island and Whakaari and Ruapehu erupt the most frequently at the moment. So if I was going to put money on a next volcano to erupt, I'd probably go with White Island. And then Ruapehu probably next most likely. Tongariro maybe coming in third. Probably Taranaki coming in fourth. Then maybe if something erupted from the Taupo area, it's very, very unlikely it would be a big boom. It's actually much more likely it would be a small boom, or even just some kind of earthquake swarm. So, if some activity did happen at Taupo, you don't need to start selling your holiday homes. The likelihood is that it would just be a small eruption would occur, because again, they're much more common than the big ones. And Auckland erupts less frequent. much less frequently than those cone volcanoes, so much bigger time gap. But probably Rangitoto, it's very hard to predict where the next Auckland eruption would be, as every time it's erupted in a new place. But except for Rangitoto, that's erupted a couple of times in the same place. So probably my money would be on Rangitoto if I was a betting man. All right.